Today on ESPN, we will be covering the physics of volleyball with your host, Kendall Hickson.
Hi everybody, I'm Kendall Hickson, and today we'll be learning about the physics of volleyball. With me here, I have Captain Christina Fergal of the PHS volleyball team. How are you doing, Christina?
I'm great, how are you?
I'm doing excellent. Okay, let's just dive into it. What will you be showing us today?
Today I'm going to be demonstrating a short and deep serve for you.
Whoa!
Hi, my name is Dr. Jacqueline Gomer, and I graduated from MIT with a PhD in physics. And I'm here today to break down the science behind the game of volleyball. The optimal way to serve the ball is to have it in the air for the shortest amount of time possible. First, we'll look at the deep serve. An important factor in the serve of a volleyball is the ball's projectile motion. The path in which the ball travels is in the shape of a parabola, as shown here. The key to a good steep serve is to have the ball go right over the net and towards the back of the court. The parabola of a deep serve would have a different shape than the parabola of a short serve, as shown here. In order to find the motion of the volleyball, we need to find the ball's projectile motion. To find the ball's horizontal velocity, we would use the formula VH equals DH times average time. And then to determine how far the ball falls vertically, we would use the formula vertical distance equals 1/2 GT squared. First, for the horizontal velocity, we'll measure from where Christina served the ball to where the ball lands in the back of the court. The distance is 18.7 meters. Also, we'll use the average time of Christina's serve of 1.5 seconds. We use the distance of 18.7 meters and divide it by 1.5 seconds to get the horizontal velocity of 12.5 meters per second. Now on to calculating how far the ball falls vertically. To figure this out, we will need to square the time in which the ball is at the apex of the serve. This is 0.75 seconds. Then we will need to multiply this by the constant of gravity of negative 9.8 meters per second squared. Altogether, we multiply that by 1/2, and from this equation we find that the ball falls a vertical distance of negative 2.76 meters from the apex of the serve. Now on to the physics of a short serve. To calculate the ball's horizontal velocity, we will use the same formula, VH equals DH divided by average time. Here we'll use the horizontal distance of 12.9 meters and the average time of 1.05 seconds. Plugging this into the equation, we find that the horizontal velocity of a short serve is 12.3 meters per second. Now on to calculating how far the ball falls vertically in a short serve. We'll use the same equation, dV equals 1/2 GT squared, to find how far the ball falls vertically. We'll use the same constant for gravity, negative 9.8 meters per second, and multiply it by 1.05 seconds squared, and then multiply that all together by 1/2. This will give us the vertical distance of negative 5.40 meters in which the ball falls vertically from the apex of the serve. At first glance, it may seem like the serve of a volleyball is a simple thing, but in reality, a lot of physics has to go into the serve of a volleyball. Now back to you, Kendall.
Well, isn't that interesting, kids? What will you be showing us next?
Next I'll be demonstrating a spike. A spike is an overhead forceful hit to the opponent's side of the court. My teammate Bree Custance will help me demonstrate this attack.
There are a few key factors that go into the spiking of a volleyball. For instance, an important factor to consider is the impulse applied to the ball once you have spiked the ball. To find the impulse, you can use the formula Imp equals momentum times change in velocity over change in time. Something to take into account when spiking a volleyball is the hang time in which the player is in the air. To find the hang time of a player hitting the ball, we need to account for the height of the jump, the takeoff velocity, and the acceleration due to gravity. To begin, we need to calculate the takeoff velocity of Christina. Here we use the distance that Christina jumped vertically, which is 0.242 meters. We use this distance to plug into the formula VF squared equals VI squared plus 2AD. Here, we're solving for VI, where VF equals 0, acceleration is negative 9.8 meters per second squared, and the distance is 0.242 meters. After plugging this into the equation, we find that Christina's takeoff velocity is 2.178 meters per second. With this takeoff velocity, we can also find the time to the top of Christina's jump. Here we'll use the formula VF equals VI plus AT. Here we are solving for t. VF equals 0, VI equals 2.178 meters, and A equals negative 9.8 meters per second squared. After plugging this in and solving, we find that the time to the top of the jump is 0.222 seconds. To find your entire hang time, you can just multiply the time that you found in the second step by 2. Here we'll use the time 0.222 seconds, multiply it by 2 to find that Christina's total hang time is 0.444 seconds.
Well, that's all the time we have today. I want to thank Christina for all her help.
Thanks for having me, Kendall. I had a blast.
Great. Okay, join us next week when we find out how fast a cheetah really is. Good night, and roll cats.
You know what it is, volleyball game. Chick, 1, 2.